we want to determine whether a vector field is conservative, and we're going to learn a very powerful theorem in vector calculus called the fundamental theorem of line integrals. It's going to be one of the four major theorems in vector calculus, and then understand the concept of independence of path. And you guys are going to love this section after looking how this will simplify the work that we just did in the previous section. Again, like I said, every new section will solve the problem in an easier way than the previous one. You're gonna like this one. Okay, so but before getting into this conservative vector fields, let's describe the different type of curves and regions. For instance, some curves can be not closed or closed. So closed, for instance, when we have like around a circle, around an ellipse, around, I don't know, maybe different paths connected that are actually turn out being a closed curve. And then we have, and it's also simple. And then we have a simple but not closed. That is, it goes from point A to B without being closed, actually. What else? What do we have? Closed but not simple. Well, the reason why this is not simple, that's because this C essentially divides this into, say, C1 over here, sharp corner, call it C2. So we would need to parameterize these two circuits here. Then what else do we have? Not closed and not simple. That's because, okay, let's call this C1, let's call this C2 with this loop, and then let's call this C3. That's because what do we have? The curve intersecting with itself, that's a C1. And then going around the loop, C2 intersecting with itself again, and then call this C3. So that's why it's not simple. Or another way to say this, we have a combination of two not closed curves with a closed curve, which is kind of weird, right? So what about regions? Well, you guys are experts in regions after double and triple integrals, right? Okay, so well, our regions, for instance, when we integrate over, I don't know, over an ellipse, over a rectangle, maybe over a rectangular region or an elliptic region, circular region, that's simply connected and simply connected region, okay? But what if we have something like those cylinders? We have like shells of cylinders. You know, when it was one of the take-home quiz questions, you were integrating in cylindrical coordinates, I believe, a solid region within two cylinders of two different radii, right? And well, the projection looks something like this. Of course, this is just a very generic representation, but it would look just like a donut like this, right? For the two cylinders. So that's what we call a connected, but not simply connected. What does that mean? Because in the end, what we care about is the boundary of this region. For instance, if we were to parameterize this curve, let's call it simply C1, all right? However, we would be a little bit in trouble if we have a situation like number 2 right here, because let's call this C1, all right? But at one point, we would have to do the following. We would have to cross in this direction, continue here, and then get out of there like this. So that makes it not simply connected. It's still connected, but not simply connected because we have more than one curve surrounding the region. One curve inside, one curve outside. Well, what about not connected, but they're simply connected individually? That means, well, we have to evaluate an integral over this region plus the integral along this other region. And what about a combination of the first two, not connected and also not simply connected individually, right? We're going to look at these regions later, especially when we get to section 17.5, Green's theorem. You'll see. Okay, conservative vector fields. So, a vector field F is called conservative on a region, whether in R2 or in R3, if there exists a differentiable scalar function, let's call it phi, such that F equals nabla of phi on that region. Again, that nabla means the gradient, all right? Then the function phi is called the potential function. And again, we already talked about this vector field back when we were in chapter 15, when we took the gradient of a function. The gradient acts on a scalar, not on to produce a vector. All right? But back then, I didn't tell you that was a vector field until we discussed it again in 17.1, that the gradient is one of the most common vector fields. But this gradient field uh, happens to be a special vector field because it's conservative. So in a vector field, it's conservative. I mean, if I give you something like, I don't know, x cubed, y, comma, cosine, xz, comma, e to the z cubed, for instance. So this vector field would be conservative if that vector field is the gradient of some scalar function. Well, what did we do to get the gradient? How do we get the gradient? The derivative. Okay, the derivative of what? Not a vector. So the gradient doesn't come from a vector. It's a vector, but doesn't come from a vector. We take the derivative of what? Not of each component. We produce components, but not of each component. So we get the gradient of some scalar function, right? Some scalar function. So if we can prove that this is indeed the partial derivative with respect x, with respect y, and with respect z of some function, well, that means this given vector field will be conservative, and we can retrieve that potential function. But again, what did we do? What do we do to get the gradient, the derivative? What do you think we're going to do to get the potential function if we find out that the vector field is conservative? Integrate, right? So be ready to integrate. Okay. But first of all, we need to test whether a vector field is conservative. So number one, a vector field which has the format M, Mi, Nj, and Pk, that is components of functions of x, y, and z, or simply x, y. So that's a vector field on a connected and simply connected region in space or in the plane, where M, N, and P have continuous first partial derivatives only. So F is conservative if it satisfies the three conditions right here. Okay? So F in space is conservative if it satisfies the three conditions. That means we need to, what's that? We need to find 6 partial derivatives, set them equal to each other in this unique way, and well, show that indeed it's conservative. However, if the vector field it's only in R2, we only need to check one condition. The m, the partial of m with respect y, and equal to the partial of n with respect x. Well, let's see this in action. Okay, let's see this in action and hopefully see what it is about. So we're given a couple of vector fields right here. F of x, y, oh, that's a vector in R2, so that's going to simplify the work because we will need to satisfy one condition. Number one, let's write this in a more convenient way because we have variables in the denominator. We write this as x to the negative 2, y, comma, negative x to the negative 1. Okay, so this will be our, let's label, this will be our m, and this will be our n. All right. So what do we need to have this satisfied? So all we need to make sure is that the partial of m with respect y is equal to the partial of n with respect x. Okay, let me use the other notation. Is m with respect y equal to n with respect x? We'll see. Okay, what's the partial derivative of the component m with respect y?
1 over
or x to the negative 2, right? X to the negative 2 equal to, what's the partial derivative of the n component with respect x? Also x to the negative 2. Is the condition satisfied? Yes. Okay, this means then f is conservative. What about number 2? Okay, letter B rather. So let's label the components. Let's label the components. In this case, it's a vector field in space. This is our M, N, and P. All right. So, but in this case, we need to satisfy 3 conditions. That means we need to take about 6 partial derivatives. All right. Okay. So let's get started with this partial derivative. So we want to know if the partial of m with respect y is equal to the partial of n with respect x. All right? So, let's see. Is partial of m with respect y equals to partial of n with respect x? Okay, what's a partial of m with respect y? So, that is x plus 2y, right? X plus 2y. And what is the partial of n with respect x? Is that 2x plus 2y? Are these partial derivatives the same? No. What does that mean? F is not conservative, and you're done. You don't need to bother and check the other conditions. The minute one of these conditions fail to be satisfied, don't bother evaluating or checking the other two. You're done. So F is not conservative. F is not conservative. Okay, what does that mean? So this means that this vector field, it's the gradient of some scalar function. That means we have, well, actually I'm going to outline the steps to find that potential function. While in this case, this vector field, it's not conservative. That means this vector field, it's no scalar function's gradient. So it's just a vector field. It's just a set of streamlines. That's all it is. But it's not conservative. It's not one of those special vector fields that are conservative. Okay, what do we do? Okay, steps to find the potential function. And guys, follow these steps. Do not do what MyMATLAB does, which is like putting components together, setting components equal, and then canceling things here and no. Don't do that. This is easier, trust me. So, if a vector field f of x, y, z with components m, n, and p is conservative, then to find the potential function, letter A, evaluate the partial integrals. Remember, that's why I asked you guys, what do we do to get the gradient? That is, finding the partial derivative of a scalar function with respect x, with respect y, and with respect z, and arrange them in a vector, all right? So that's because we're going to do the reverse. Now we're going to do the backwards process, that is retrieve the original function, the potential function, by means of partial integration. So what we took the derivative of with respect x, and now we're going to integrate it with respect y. What we took the derivative of with respect y, now we're going to do integrate it with respect y. And lastly, what we differentiated with respect z, we will integrate it with respect z, right? Okay, letter B, and this is the tricky part right here. Just consolidate the results. Do not write any duplicates. Do not combine them. Don't feel compelled to combine them. I'll show you how this is going to work. Now, if the vector field given is in R2, that is in 2 dimensions, all we need to evaluate is the integrals with respect x and with respect y, because we don't have that z component, right? The third component. Okay. Example number 2. Consider big F of x, y. That's actually a vector field in R2. 3x squared y squared in the direction of y, and 2x cubed y in the direction of j. Number 1, prove that this vector field is conservative, and then find the potential function. All right. So again, you might want to label this. This is our m. This is our n. All right. So we need to show that the partial derivative with respect y equals the partial derivative of n with respect x. Okay? Is that the case? Let's verify that. Okay, partial derivative of m with respect to y. Okay, that'll be the derivative of y squared, which is 2y, right? But 2y times the 3x squared, isn't that 6x squared y? Equal, okay, the partial of n with respect x. The derivative of 2x cubed y, that'll be the derivative of 2x cubed, which is 6x squared y. Oh, it's the same, right? 6x squared y. So, check. It's conservative. So now this means that this vector field comes from taking the partial derivatives of a scalar function, that is taking the gradient. So what are we going to do? Partial integration. The integral of m dx that equals the integral of 3x squared y squared dx, whose integral, okay, that'll be the integral with respect to x, the integral of 3x squared with respect to x, that'll be 3x cubed over 3. Isn't that just x cubed times y squared? Okay, so that's x cubed y squared. However, what do we do when we evaluate an indefinite partial integral? Plus c, plus c1? Not c1. Huh? Plus c. Huh? Cm? Not m? No, not m. Not all real numbers, no. C of, because we're integrating with respect x, right? We're holding the other variable constant, right? So this has to be a c of y, right? A c of y. Okay. What about the integral of n with respect y? That equals, what's that? The integral of 2x cubed y dy. And the integral of y with respect y, that's y squared over 2 times the 2's cancel. That's going to give us what? Oh, another x cubed, y squared plus c, what's the c? C of what? C of x. Okay? Alright, so let's write down the potential function. Phi of x of y, that equals, again, do not just write down one instance of every term. Well, in this case, the only term we have is the x cubed y squared. But do not combine them together. Just bring one instance of each. And now, just ignore the c of x and c of y. Now, here is the thing. Another comment I would like to make here. So this is what you would be expected to fill in the blank in MyLab. The potential function without anything. However, how do we get that result? Did we get that result out of an integration problem? Out of an integration process, rather? But what are we supposed to add when we integrate via indefinite integral? Plus c, right? Which is not there. So that's the issue I have with the textbook, with the MyLab part of the problem, that it doesn't ask for the concept of integration. But what does that mean? Okay, this c of y, c of x can be combined to obtain some plus k, right? So we all know that there's a concept of integration involved somewhere, right? So that's our first example of finding the potential function. Now take the gradient of this. Take the gradient. What's the gradient? The derivative with respect to x, that's 3x squared to y squared. The derivative with respect to y, that's 2x cubed y. Isn't that the same original problem? Right? So that's going back and forth between a potential function, a scalar function, and its gradient. Right? That's all we're doing. Again, a vector field is said to be conservative if it is some scalar function's gradient. Right? Let's take a break.